In this lecture, we will be going over principal component methods. The reading for this lecture is Chapter 6 in An Introduction to Statistical Learning with Applications in R, titled Linear Model Selection and Regularization. If you have not read this, please pause, go read it, and come back. This lecture will be going over three primary topics. First, we will be going over principal component analysis, or PCA. Next, we'll go over principal component regression, and we'll end with a discussion on partial least squares. In order to understand principal component regression and partial least squares, you have to have a basic understanding of the concept of principal component analysis, or PCA. PCA is a method for dealing with high-dimensional data sets. It's a way of reducing the dimensionality of a data set of interest. Now, as a reminder, when we talk about dimensionality, we're specifically talking about the relative proportion of observations to variables in your model. As n approaches p, or as you get as many variables as observations, the dimensionality increases, the model becomes more flexible, its variance increases. So that the flexibility of a model with 15 parameters is going to be much more than a model with just one. And this becomes a problem in the fitting process because as you increase variance, you lose bias. You lose the ability to generalize your results to not samples outside of your training set. Now, the fundamental question we're going to explore in this lecture is how do you reduce the dimensionality of your model? How do you find a way of reducing the correlations across variables and only looking at the lower dimensional projections of your data? In prior lectures, we went over reducing the dimensionality of your model by doing feature selection. So example, best subset selection or stepwise selection routines where you compare in a competition the fit of different models with different numbers of parameters, typically using bias-adjusted criteria. We also went over ways of using sparsity constraints during the model fitting process itself, with ridge regression shrinking or making more conservative regression coefficient estimates, lasso doing feature selection, and elastic net doing something in the middle. But an alternative to reducing the dimensionality of your model is to reduce the dimensionality of your predictor variables themselves. Compress essentially the dimensionality of X. And that is where principal component analysis, or PCA, comes in. With PCA, what you're trying to do is reduce the dimensionality of X itself. So essentially, the goal of PCA is to learn how to take your data X, find the correlations in X, and get projections of your data, which we'll call Z, in that low dimensional space, such that every variable in Z, every column in Z, is independent of every other column in Z. We call this Z here the low dimensional projection, or the component. X here is your original data, so this X of J here is a column vector of a particular variable in your data set. And the goal of PCA is to learn this component loading matrix, phi. Essentially, it is a unsupervised algorithm that learns phi and allows for you to reorder and linearly reorganize X into a series of independent variables Z. You've seen some ideas similar to this in the lectures on regression. Essentially, what PCA is doing is compressing your data. So for example, the first component in every learned PCA explains the most variance about the relationships between two variables. So let's say we're just looking at x1 and x2. We just have two variables. It's very simple. You will always have as many principal components as you have variables. So in a PCA with two variables, you'll get two principal components. If we look at the distribution of a hypothetical data set here, so x1 and x2, the first principal component is akin in some ways to the regression line. It is the line through the joint distribution of x1 and x2 that explains the most variance. The second principal component is linearly independent. It is orthogonal or perpendicular to the first. So together, z1 and z2 should explain the most variance, or all of the variance in your data. And actually, I take that back. It doesn't should, it does. The goal of PCA is just to learn these low dimensional projections and restate your data in this space. The algorithm itself is relatively simple, and there are many variants of it. I'm presenting one variant of doing principal components analysis. There are others. One of the more common ones, which is known as singular value decomposition, I'm not going to go over, but the flavor is pretty much the same. So for typical PCA, the goal is to first find the first principal component loading, which you do by finding the projections or the column on phi that maximizes the covariance of x. So you're looking for the argmax of x transpose x weighted by some estimate of phi. Then you take the residuals after you've learned that first principal component. So I have phi here, and I'm going to weight it by x, and then I'm going to subtract that principal component from x and to learn a new x hat m. And then you calculate the next principal component from there. So I have x hat m, which is my version of x that's removed the predictions of the first principal component. I repeat the process. I find the phis that best explain or maximize the covariance between x hat m and itself, or within x hat m. And you keep doing this until you've gone through as many iterations of the algorithm as you have variables in your data set. So you repeat steps 2 and 3 until m, the components, equals p, the number of variables you have in your data set. In the end, you will explain 100% of the variance in your data. So let's go back to the bivariate example for a second. Here's my x1, x2. The projection that best explains all the variance in my data is z1 here. So I will project all of my observations down to z1. This is akin to taking the residuals. Those are now the projections. Where each one of these lines intersects the z1 line is the projection of each data point into my component space. Now I take those residuals, which would look like this, and in a simple bivariate case, the line that best explains the variance between z1 and my new projection of x is z2, which is just the mean of x2 really, or x hat 2. So you've got now this clean way of accounting for all of the variance in your data set, and in this case, z1 and z2 are perfectly independent of each other. Let's think about this with a more complex example. Let's say you have a 10-dimensional feature variable matrix. So P equals 10. And just for our example today, let's say that you have 15 observations. So N equals 15. When you run PCA, what you'll get is 10 principal components and an estimate of the percent variance explained by each component. Now remember, they're all linearly independent, and they start with the component that explains the most variance in your data. So the first principal component will always explain the most. The next one will explain slightly less, slightly less, slightly less, etc. And it usually falls off in this curved pattern here. Now, if we look at the cumulative variance explained, so we ask how much variance has been explained up to principal component I. So in the first case with principal component 1, that's the same as just the variance explained by principal component 1. The cumulative variance at principal component 2 is the variance explained by principal component 1 and principal component 2. The cumulative variance explained by the first three components is the variance explained by the first, second, and third principal components. And then you just keep going through this. You get a line that looks like this. And by the time you get to principal component 10 in this example, 100% of the variance is explained. If you've been paying attention, you'll remember that I started this portion of the lecture by saying that PCA reduces the dimensionality of your data set. But I'm also showing you here that when you have 10 variables, you'll get 10 principal components. So how is the dimensionality really reduced? Well, typically when you're doing PCA, you don't use or you don't utilize all of the principal components. You assume that at some point the principal components are just capturing noise. Typically what's done is to set a particular alpha or percent variance that you want explained and only take those subset of principal components that explain that much variance. So for example, let's say you want to just take the first n components that explain 95% of the variance. Well, in that case here, that means you'll take the first 5 principal components because those cumulatively explain 95% of the variance. The last 5 components just really explain noise. They're not really explaining that much variability in X to be meaningful. In this way, you've changed a 10-dimensional problem and made it a 5-dimensional problem. Students in psychology, particularly social psychology, will find this logic of PCA very familiar because things like factor analysis are very common in that area or those fields. And PCA and factor analysis are fairly similar in their conceptual framework. So for example, I showed you with PCA, what you do is you take a n by p matrix and you learn an n by m matrix, and which is in this case, m is the number of meaningful components in your PCA. And the last example, m would be 5. Factor analysis is the same logic where you have a p by n matrix. I'm showing the transpose here in the normal way we talk about factor analysis. And you're supposed to learn some component loading matrix, L, that projects a set of factors, F, into X space. Notice that F and Z are essentially the same dimensionality. They're just transposed. So the logic's the same. But with factor analysis, the factor loading itself, you have to pre-specify M. In non-exploratory factor analysis, you don't choose M based off of the performance of the variance explained. You have to start with an assumption of the low-dimensional projection. Whereas PCA, you get all components of your model, and you look at the percent variance explained and reduce the dimensionality that way. So in this way, PCA is better for exploratory analysis when you don't have a good a priori understanding of what the low dimensional projection of your data will be. Factor analysis is much better for hypothesis testing because you start with an assumed low dimensional projection of your data. PCA will explain all variance in X. So if you set M equal P, where you get all components as you have variables in your data set, you'll explain all of your variance. Whereas factor analysis, because you have to preset M, you will typically only explain a portion of the variability. Also, PCA does not assume that you necessarily have a low dimensionality in X, whereas factor analysis forces that assumption on X. For example, if every column in X, every variable you have in X, is linearly independent of one another, then Z and X will look almost identical in principal components analysis. It's not a requirement to run PCA that they be a low dimensional projection. But with factor analysis, when you specify up front the low dimensional number that you're looking for, you're automatically assuming that is the low dimensional nature of the data. You assume that X has a lower dimensionality than it does. So PCA will estimate that and tell you that, whereas factor analysis, because you have to start up front, will largely start with the assumption that there is a low dimensional projection to your data. But like I said, they're qualitatively similar. PCA is much more commonly used in machine learning and statistics, so we're going to keep focusing on that. One way that PCA, or principal component analysis, is helpful is in reducing the dimensionality of a linear regression model. You can use PCA to essentially do a feature selection on X by focusing not on X itself, but the low dimensional projection of X in principal component space. That process is known as principal component regression. Principal component regression, or PCR, has the goal of reducing the dimensionality of your predictor variable set, first using PCA, and then use those components, or the strongest components that you've observed, as your predictor variables. Essentially, you look at the best subset of principal components that explains the most variance of your data, and you run your linear regression algorithm on those as opposed to X itself. So it really is just principal component analysis and linear regression paired together. The typical form we talk about principal component regression in is every prediction for y hat I, comes from a set of regression coefficients, which we're showing here as theta hat, on each relevant principal component, zi. So for principal component regression to work, you have to select the subset of components that are meaningful. So in this case, k should be less than p. And you just want to select the components that explain 1 minus alpha % variance in X. The regression coefficients, theta, we're showing as theta hat here, they are effectively the same as the regression coefficients we see in linear regression. I'm just using a different term here so that conceptually it makes sense that you're learning a linear regression not in your data space X, but in principal component space. And Z here is your principal component M. So the algorithm, or the way that you do principal component regression, is to start with calculating your PCA, learn the component loadings for your data set, identify the k components that explain 1 minus alpha, or typically 95% of the variance in X, and then run a regression model using those k components identified in step 2. That's it. What you get out is a prediction of y that's very similar to what you had before. In this case, the normative change is that instead of your prediction of y being a f hat of X, it's your prediction of y is f hat of Z. Now the beauty of working with PCA approaches and PCR is that you actually have this easy ability to learn the model in principal component space, but project the model back into your data space. You can actually determine the regression weights in X that best resolve the bias variance trade-off via the coefficients that you learned in Z, the principal component space. Effectively, what you're doing by forcing your analysis, your linear regression, to work on the subset of principal components that are most meaningful, remember, each component is linearly independent of the next, so it meets that core assumption of linear regression. So you're automatically learning the best model that balances the bias variance trade-off. But because you can project your components back into your data space, you can show what that model looks like if you were looking at it in your raw data space as opposed to principal component space. How does this work? Well, remember, this is the logic of PCR, and you're learning your regression coefficients, theta hat, from your principal components. Also remember that your principal components are just a linear combination of your data itself. So each Z is actually represented by theta hat X, which means that we can rewrite the principal component regression model this way. Just replace Z with the linear projection of the data. And if I just move the sums around, the sum of M1 to K, so we're all M relevant components that you have in your model, if you multiply the regression coefficient for that component by the component loading vector, phi, that gives you beta for that particular variable. It's a nice, beautiful linear combination of variables. So that the best regression model for a high dimensional data set is really just the sum of all the relevant learned regression coefficients in principal component space times their component loadings for that variable. And this is true even when n comes really close to p. When you have a really high dimensional or highly flexible model, you can still learn the best regression coefficients for your data. Now, the key here is that you're going to get a regression coefficient for all of your variables. So you will have p regression coefficients. But it is the best balance of regression coefficients that you could get that manages the bias variance trade-off without actually removing variables themselves. You're not removing anything. You're just learning your model in the low dimensional space of X. You're essentially learning your model in this subspace of your data where your correlations exist. Now, there is an assumption here that the low dimensional space of X itself, how you look at the principal components in X, is independent of how X is related to Y. Your principal components might have some correlation to Y, but how you learn your principal components in PCR is assumed to be independent of the covariance between X and Y. Now, that might not always be the case. There are some cases where the low dimensional projection of X depends on X's relationship to Y. To account for cases like that, there's a method known as partial least squares. Partial least squares, or PLS, is just a slightly different flavor of principal component regression. But instead of first looking at the lower dimensionality of X and then regressing on Y, what you're going to do with PLS is find the lower dimensions in X that maximize the covariance with Y. You learn both the loading between X and Z at the same time that you learn the correlation or the regression between Z and Y. So this is the normative form of the PLS model. Every observation of Y is a sum of both all of your P predictor variables and all M or all K principal components that lead to them, or at least the subset that are relevant. So again, your number of variables in X is P, number of variables in your principal component is K. You're going to learn your regression coefficient, so that's why there's a hat over this. But unlike PCR, you actually have a hat now over phi, which means that phi becomes a free parameter in your model fitting process. Essentially what you're doing is you're introducing now a constraint on how you learn phi so that it maximizes the likelihood of your data. It minimizes the residual squared error between Y and your low dimensional space. In this case, your principal components and your regression coefficients are all learned in one fell swoop. Now, in most cases, you're going to get qualitatively similar results between PLS and PCR. What ends up happening is that the Let's say you have a particular x and a particular y, and I'm just looking at the relationships between one of the variables here this is just an illustrative example. You might learn a regression line with PCR that looks like this, but the regression line you get with PLS has a slight deviance from that. They're all going to be basically giving you similar ways of managing the bias variance trade-off, but the important part with PLS is that it should explain more variance in Y than PCR. And so it's going to be important to even though that PLS and PCR produce qualitatively different results, you're going to want to look at the percent variance explained by both. Now, the nice thing here is that PLS and PCR on the same data set have the same dimensionality. So in that case, you just would want to go with the model that best, minimizes your residual squared error. But in some contexts, PLS can give you a big boost in your predictive accuracy and your bias variance trade-off over PCR. So they're not really a ground truth or a good rubric for when to use one over the other. You might want to just consider using them both in tandem to understand what's the best model for your data. Now, just taking a step back, I hope this lecture has convinced you that principal component methods, like PCR and PLS, offer an easy way of resolving the bias variance trade-off in high dimensionality contexts by leveraging any correlational structure in your predictor variables X. These are very effective ways of managing the bias variance trade-off without actually doing feature selection itself or imposing some sparsity constraint on your regression coefficients. Remember, you can recover regression coefficients for all the variables in your data, even if you have a high p relative to n. But that projection will maximally balance the bias variance trade-off because you've learned it in your low-dimensional space. So in this way, these principal component methods offer a really intuitive way of understanding the best form of high-dimensional models.